All right, today, do need to end class early again. So I'm going to go through two main examples and then we'll be done. CP can be your first page again. First example I want to do is another nonlinear system. So we're going to think about drawing phase portraits by hand as much as we can with technology where necessary, using the ideas of Nullclines still, but also this new idea of linearization. And then I want to look at an example with linear algebra regarding looking at orthogonal decompositions and something called the Gram-Schmidt process, which is related to your homework due tomorrow, I believe. I think I put a problem like that in there. So what I'd like to do is, it's problem number 25 in section 5.1. Here it is. Here's the system right there. I'll go ahead and write that down. And you'll notice there's an unspecified parameter in there, an A. So this is going to be a bifurcation problem. And your main Diff problem due tomorrow is really, in the end, a bifurcation problem as well. We've got a nonlinear system. It's really a one parameter family of functions, of systems here. dx dt equals, go ahead and use subscript notation here to emphasize the parameter. I'll call the right-hand side here initially f sub a of xy is y minus x squared plus a. dy dt's right-hand side does not depend on a. I mean, I could call it g sub a anyway, but I'll just call it g sub x comma y. That was y plus x squared. You should certainly be able to convert this to a vector field. If you let capital vector y be a vector whose components are little x and little y, then this is dy dt equals capital F vector of y vector, which is an autonomous vector field. There's no t's on the right-hand side. But it does have a subscript, say, of a. And just take these right-hand sides and make them the components. Y minus x squared plus a for the first component and y plus x squared for the second. I also could have written initially little f sub a of xy for the first component and little g. Okay, so it's a nonlinear system because, well, we've got two nonlinearities, the minus x squared there and the plus x squared there. And what the first thing you should say in your mind to yourself when you see a nonlinear system like this is you should say, there are probably no formulas for any solutions except perhaps any equilibrium solutions. Or if you're lucky, there might be some straight line solutions, but that's pretty rare. So I have to either use numerical methods like two-dimensional Euler's method or something better, or mostly for us, qualitative approach, try to draw the phase portrait in the phase plane with the help of Nullclines, equilibrium points, and linearization. And that's what we're about to do. Let's think about the Nullclines first. Good place to start. The X Nullcline. In section 5.2 of our textbook, the textbook finally gets to talking about Nullclines, but we've been practicing them for a long time. That's where dx dt is 0. Solutions cross X Nullclines with vertical tangents, or else they are equilibrium points. That's where the first component of the vector field is 0, which for this example means, of course, this thing is 0, which for the purpose of drawing the phase plane, it's probably good that when you set this equal to 0, you solve for y as a function of x. So we'd have to, if you imagine with me here, setting that equal to 0, we'd have to add x squared to both sides and subtract a, and we'd get y equals x squared minus a, whose graph is a parabola opening upward with vertical intercept at a, negative a, right? vertical intercept will be at negative a, whatever a happens to be. Why nullcline? Where dy dt is 0. That's where the g function is 0. Which means for this example, y plus x squared equals 0. That's going to be when y is negative x squared. A single parabola opening downward, going to the origin. I'm missing purple pens. I like purple pens. Where's my purple? Where x and y nullcline intersect, you're going to have equilibrium points. Think about this here. You're going to have to think about cases. Negative a is the vertical y-intercept of this graph. If negative a is positive, meaning if a itself is negative, that'll be above the horizontal axis and it won't even touch this graph. There won't be any equilibrium points. On the other hand, if negative a is negative, a is positive, these two graphs will cross two spots. Can you visualize it without drawing it? Upward pointing parabola and downward pointing parabola. When a is 0, they'll touch at the origin. So it seems like there's a bifurcation at a equals 0. That's a bifurcation in the number of equilibrium points. We could also perhaps have other bifurcations in the types of equilibrium points. That's theoretically possible, at least. But it seems like certainly we should think about cases where a is negative, positive, and 0. Let's think about the case where a is negative first. That'll have no equilibrium points. Because again, if a is negative, then negative a is positive. And the x nullcline will be above the horizontal axis and not touch this graph at all. The x nullcline, x squared minus a when a is negative. For example, if a were negative 1, this would be x plus 1 in the end. It's going to be up here. Cross that vertically. The y nullcline, no matter what a is y equals negative x squared. Cross that horizontally. These two distinct nullclines are not crossing at all, so there's no equilibrium points. But we do want to try to still draw the rest of the phase portrait. We want to draw in some solutions and get an idea of the behavior of solutions. That's the point, right? If this had an application, the point of the application would be what happens to solutions as t goes to infinity. So now you need to think about the signs of these functions. Are they positive or negative in these three different regions? You want to think about the nullclines as separating the plane into three different regions. They are not separatrices like I talked about on Friday, because separatrices are actual solutions that separate the plane into pieces. These are nullclines, not solutions. They're helpful because they're just helpful for drawing the picture. That's the point. But they do separate the plane into regions where dx dt and dy dt could have different signs, SIG and S, positive or negative. Oops. So dx dt is positive when this thing's positive. Imagine making that bigger than 0. That's equivalent to saying y is bigger than x squared minus a. Dx dt is positive when you're above this x nullcline. Dx dt is positive. Up here, solutions move to the right. And dx dt is negative when you're below this x nullcline in these two regions, here and here. leftward motion of solutions. On the other hand, dy dt is positive when this thing's positive. Certainly that's true when x and y are positive. There, it's also true when x is negative but y is positive over here. In fact, it's true when you're above the red graph. dy dt is positive above the red graph, it's negative below it. Does that make sense? That's dy dt right there. It's going to be negative, for example, when y plus x squared is negative, so y would be less than negative x squared, which is going to be below the graph of y equals negative x squared. So now you start just picking some initial conditions. You know, you could pick one and say here, it's got to head to the northwest, and it's going to have to cross the x nullcline at some point, and then head to the northeast. Could it possibly cross the x nullcline again? You think about it for this example, it can't. Because if it were going to cross it again, it would have to cross non-vertically. It's going to have to go to the northeast here, but it's never going to cross the x nullcline again. Pick another initial condition about there. It's going to go to the northwest. Seems like it would probably be forced to cross the x nullcline at some point, maybe there, but once again, never again. Pick one down here far enough. It's got to go to the northwest, but it's going to cross the y nullcline, and that's going to cross horizontally. And then go to the southwest, and it never, well, that one could cross the y nullcline again. It's not clear whether it will or not. That would be a little bit mysterious. That would be, further investigation would be necessary to know whether that's going to cross the y nullcline again or not, because it could just keep going to the southwest without crossing it, or it could cross it again. Certainly if it was up high enough, it seems intuitive that it should cross it again before going back to the northwest. Something like that probably happens, it seems. And you could confirm it with stream plot. But I do wonder whether or not, if you were down far enough here, whether you might get some solutions that never cross the y nullcline again or not. That it's an investigation you'd have to do. Maybe it does, maybe it doesn't. Do I have a guess? I'm guessing it probably does cross it again. But in theory, it's possible it doesn't at some point if you go down with your initial condition far enough. Some solutions got to head up this way and I guess kind of go between the two. I mean, there's going to be some that cross the x nullcline there, say, and then other ones that cross here, say. You might wonder, are there ones that sort of just keep going forever and ever off that way without crossing the green x nullcline ever? That's possible. That would take more investigation as well. So there's a basic drawing of the phase portrait in the phase plane without knowing everything about it. There are open questions. Are there any solutions that head off this way forever and ever without crossing this x nullcline? Including, do these solutions head up this way without crossing it? Or do they ever cross it again? Are there solutions down here far enough that never cross the red one again? It's not clear. But this is good enough for us, I think, for this class. A is 0. The red and green do touch just at the origin. So the origin is going to be an equilibrium point. do make, if you haven't been in the habit of doing so, do make big dots at your equilibrium points. Not that points really have any area, but we're just trying to emphasize there's an equilibrium point there, so it's good to draw it big. The signs of df dt and dy dt are going to be consistent with what they were before. So positive for df dt and dy dt up there, in here and over here, positive for dy dt, but negative for dx dt. And down here, negative for both. So you get some solutions that look like this, say. Go up high enough, some solutions that look like this. If you started close to the equilibrium point, but to the left of it, you have a solution that looks like this. Should seem intuitive without proof that there might be some initial conditions along some curve, maybe one of them is right here, that head, well, not necessarily straight toward the origin. So it's not necessarily a straight line solution, but do go toward the origin as t goes to infinity. That should seem somewhat intuitive, but it's certainly no proof. And probably also one kind of going away from the origin. Though that one going away would have to cross this green one, I think, before going this way again. It's unclear what kind of equilibrium point the origin is, isn't it? Is that a sink or a saddle or? It's hard to say what it is. And that is actually the case. It's kind of a hard to classify equilibrium point. Exactly what's going on there. We'll see if this linearization idea helps or not here in a few minutes. Well, that's the basic picture. And then there's the case where A is positive. Where we finally get, well, we get two equilibrium points that maybe, that I think are going to be easier to classify with linearization. Once again, there's our y nullcline. Now our x nullcline goes below the horizontal axis. So it crosses the red one at two spots. And so there are two equilibrium points here and here that we could try to find the coordinates of, and I imagine we can. But for the moment, let's try to make a drawing here. Once again, df dt is positive when you're above the green parabola and negative when you're below. So dx dt is positive here. It's also positive in this wedge here. df dt is positive in here. Rightward motion. Even though we're below the red graph there. On the other hand, df dt is negative when you're below the green graph, down here, and down here. Leftward motion. dy dt is still positive when you're above the red graph and negative when you're below it. I should have been using purple. Positive up here, positive here and here, but negative below the red graph, downward here. Sorry, this is hard to see. And downward here. So some behavior is going to be somewhat similar as before, say like this. And like this. Oops, it's not very good. and like this. Those are kind of similar to behaviors before. But new behaviors, well, you'll still have a solution that heads probably toward this one. And the ones, by the way, that are heading toward the equilibrium point are example of separatrices, plural of separatrix. That's a separatrix solution. It's not, it might look very straight on the computer. I didn't draw it straight, but it might look pretty straight on the computer without necessarily being technically a straight line solution. But something new is happening in the middle here. Southeast motion of solutions. So for example, if your initial condition was right here, say, let's go southeast, it looks like you got to head toward that equilibrium point. Well, okay, you could head toward it. You also could go above it and go off this way. You also could go below it and go down this way before heading over here. So it's getting a bit more interesting. If you think about this initial condition here and let time run backwards, so to speak, as t goes to minus infinity, it seems like we'd have to head off maybe toward this equilibrium point there. As t goes to minus infinity, so I'd have to put the arrow still going to the right. Seems like, without filling in a ton more here, this point right there is some sort of saddle point. Maybe got solutions like that too. And this one's some sort of source. That seems about right, looking at that picture carefully. This one seems like it's some sort of saddle point on the right and some sort of source here without, I mean, I could keep trying to make more in the drawing here, but maybe that would be somewhat good. Maybe even a spiral source, that could be spiraling there going on. But how do you know for sure? I mean, you can try the technology, zoom in on spots, you can see what you see. But how do we tell by hand, say? What did people do before they could visualize things on programs like Mathematica or something else? They had to use this linearization idea. So I briefly talked about linearization last time. At the origin is throwing away nonlinear terms. Somebody who's watched the lecture from last night, if you're not at the origin, what do you have to do instead? A certain matrix starts with J. Jacobian matrix is something you have to compute. What is a Jacobian matrix? Our goal is to try to understand the behavior of solutions near equilibrium points for this nonlinear system. We have to linearize near the equilibrium points. Essentially, it's like a generalization of linearization in calculus, where you found the derivative, plugged in the point, and found the equation of a tangent line. Remember doing that in Calc 1 and even in Calc 2? Tangent line approximation. That's what we're doing here, essentially, except it's higher dimensional, and so you can't visualize it so easily. The Jacobian matrix, J, is a kind of derivative. In general, it depends on what the point is, so it's really a function of the point. It's in this case, for a two-dimensional linear system, it's a 2x2 matrix whose first row consists of partial derivatives of the first component of the vector field with respect to the two variables. Partial derivatives. The derivative of f sub a with respect to x, and the derivative of f sub a with respect to y. Using partial derivative notation here because, well, there are more than one independent variable, and so it's traditional to do so. You should realize that partial derivative notation is arbitrary. I mean, ordinary kind of D's could be used instead of curvy D's. Nothing magical about the curvy D's. It's just highlighting to you, hey, this is a partial derivative. That's all it's doing. But even though multivariable calculus is not a prereq for the course, you know, actually computing these things is still, I mean, still relatively straightforward. You just, when you compute this partial derivative, you just pretend the y is constant. When you compute this one, you just pretend the x is constant. In the formulas for f and g. So the partial derivative of f with respect to x, treat the y and a as constants. The answer is just negative 2x. Partial derivative of f with respect to y is just a 1. Negative 2x and 1. Nothing involving a, actually. Won't always happen. Sometimes it could involve an a. Like if, for example, there was if this a was an a times x, then the partial with respect to x would include a plus a term. So this could depend on a, but it looks like it's not going to here. And for g, its derivative with respect to x is 2x, and with respect to y is 1. Positive 2x and 1. So in this case, this Jacobian matrix really doesn't depend on y either, but it could have. A more complicated example, it could have. What do you want to do with this thing? You want to evaluate it at the equilibrium points. That's what you want to do. And then you want to consider the linear systems corresponding to those matrices and classify the equilibrium point for those. And it probably will tell you something about the nature of these equilibrium points, at least in the case where a is positive. Let's consider that case where a is positive. A is positive. So we're in that case. Equilibrium points, where are they? I'm trying to solve a system of algebra equations. Y minus x squared plus a equals 0. Y plus x squared equals 0. You can just do it by substitution. This means y equals negative x squared, which can then be substituted into there in place of y. If you do so, you get negative 2x squared plus a equals 0. So x squared equals a over 2. Add 2x squared to both sides and divide by 2. So x is plus or minus square root of a over 2. And the corresponding y's are the same. Negative that thing squared. The plus or minuses will go away, but I still have the minus in front. We got minus a over 2. So the equilibrium points in the case where a is positive are square root of a over 2, comma, negative a over 2, and negative square root of a over 2, comma, negative a over 2. You got to plug those things into the Jacobian matrix now. Because again, the goal is to find what's called the linearization, the linearized system near these equilibrium points. The matrix for that linearized system is going to be the Jacobian matrix. By the way, not everybody uses a J for the Jacobian matrix. Some people call it D because it is kind of a derivative. But in honor of Jacobi, call it J. So what's that going to be? Again, this only depends on x. So actually the negative a over 2 won't matter. We'll be plugging these x coordinates in for x here and here. j of positive square root of a over 2 comma negative a over 2. The upper left entry was negative 2x. So I'll get a negative 2 root a over 2, which does simplify to negative root 2a, if you like. And a 1, and then a positive 2x, positive root 2a and 1. And if you plug in the other equilibrium point, you replace x with negative root a over 2. And the signs of the numbers in the first column change. It becomes positive root 2a, and this becomes negative root 2a, and the ones stay the same. Fastest way to try to classify the points now is to use the trace determinant plane. For this example here, the trace is 1 minus root 2a, and determinant is negative root 2a minus root 2a, which would be negative 2 root 2a. And the fact that the determinant is negative means the trace is irrelevant. It's a saddle point, because in the trace determinant plane, d is negative, so this point TD with these coordinates will be down here. Okay, a is some fixed positive number. You could pretend a is 2, for example. If a were 2, this would be 1 minus square root of 4. 1 minus 2 is negative 1. And this would be negative 4. It's negative. Whenever the determinant's negative, the equilibrium point's a saddle point. In the trace determinant plane, the point with these coordinates is down here. Hey, yeah, that looked like a saddle point. Are these solutions that are the separatrices, are they straight line solutions? No, but they will be tangent to eigenvectors of this matrix for your eigenvalues, one of which will be a positive real eigenvalue and one of which will be a negative real eigenvalue. So by finding the eigensystem for this, say with technology, you could then try to draw this more accurately even by hand. Although, sorry, I mean, using technology here. I mean, you could try to find the eigenvalues and eigenvectors without technology. It's not going to be very pleasant looking. Yeah, I mean, probably best to use technology to help you, even if you're still trying to draw by hand. I said this one's some sort of source, seems. Is it a spiral source or a non-spiral? It kind of looks like it might be spiral. Like in complex eigenvalues, perhaps with positive real parts. Can we confirm that? We could try. Trace is 1 plus root 2a. Determinant. Oh, okay. Okay, the determinant is actually going to be this. Yeah, in the trace and determinant plane, we are going to be up here where the origin is a source. It's not clear if it's a spiral or not. Are we above or below the repeated root parabola? That's not so clear. If d equals t squared over 4 or 4d equals t squared, you could try to figure it out. What's t squared over 4? Maybe I should just do t squared. T squared, 1 plus root 2a squared is going to be 1 plus 2 root 2a plus 2a, which is bigger. Well, okay, it's not so clear. Is this bigger than 4d or not? There's d. It's certainly bigger than d itself, but is it bigger than 4 times d? I'll put a greater than question mark 4D. It's probably less than 4D. Put greater than or less than question mark 4D, which is 8 root 2a. It's not super clear. Maybe it depends on the value of a. Definitely a source. Whether it's spiraling or not, it's not so clear. It could depend on the value of a. I could take the time to try to figure it out. I think I'll stop there as far as calculations go, and let's just use stream plot with manipulate and see how it looks. So I'm going back to the original system now and effectively plugging this vector field into Mathematica with stream plot and to animate it with manipulate. Type it as fast as I can, make it fairly minimal as far as how nice a looking picture it is. My animation parameter would be the A. Vector field, first component is 1 minus x squared plus a. Second component is 1 plus x squared. There's when a is negative. I let a increase. When a becomes positive, there are two equilibria. I did not draw them in there. I didn't take the time to do that, but they are there. There's one right about there and one right about there. See where I'm pointing? Right? Look where I'm pointing. Right there, it looks like it's a spiral source. One right about there. I could draw the Nullclines on and I could draw the equilibrium points. I'm just not taking the time to do so. Looks like it's probably a spiral source, but you can't really tell for sure just by looking at this. You'd want to think about those eigenvalues and eigenvectors more carefully. Think about the trace-determinant plane more carefully. Okay. So it's a long process. Each problem is pretty long. Use technology to help. This could make for a take-home exam problem. Something similar. I do still want to end class early today. Technically, I have 28 minutes. Let's just do a fairly quick example with the Gram-Schmidt process. So, sorry again about these PowerPoints when they're on max. The typesetting doesn't come out right. This is supposed to be like an RN there. It happens to me too. I have these problems, I always made it on Bethel's computers, but then it doesn't look right on my Mac. The Gram-Schmidt process is a way of constructing, it's called an orthogonal basis for a given subspace of Rn. Given any basis of a subspace, try to find an orthogonal basis for that subspace. Turns out to be very useful, okay, to be able to do such a thing. In part because of the orthogonal decomposition theorem, which I'm not going to spend time with in class, but is in the lectures. So it's a process, it's an algorithm. Let's just do it in the simplest possible case where W is two-dimensional. And I've got a basis of two vectors. We'll transition back and forth here. Let's say W is the span of two vectors in R3 that are not parallel. You don't want them to be linearly dependent, at least if you want it to be a basis. Oh, how about 1, -1, 2, and -1, 2, 3. This is my notation in the PowerPoint. This is my x1 and my x2. Notice x1 and x2 are not orthogonal. Their dot product is non-zero. x1 dot x2 is going to be -1 minus 2 plus 6. 3, non-zero. So they're not orthogonal. They do have an angle between them that can be taken to be less than 90 degrees. Positive angle less than 90 degrees because their dot product is positive. So they point generally in the same direction because the dot product is positive. Again, the goal is find an orthogonal basis for the same subspace. This is going to be a plane to the origin in three-dimensional space. It's a two-dimensional subspace of R3. These two vectors do form the basis for it. The V's are going to be your orthogonal basis. The first step is just to let V1 equal X1. Very easy. The first vector in your basis is the same as the first vector in the original basis. Second step, which for an example that's two-dimensional is the last step, is to let V2 be X2 minus, oh boy, projection vector of X2 along W1, where W1 is the span of V1. So W1 is the line to the origin parallel to V1. Do this calculation. W1 is the span of V1. It's a line to the origin. V2 by that formula, you could reason out this formula geometrically, but it's easy to forget. X2 minus the projection vector of X2 along W1, which is a line, so it's along that line. Going back to formulas for projections way back near the beginning of the course, first couple weeks of class, I think. That projection vector can be taken to be X2 dotted with X1, which is the same as V1, divided by V1 dotted with itself times V1. And yes, V1 is the same as X1, but it's probably better to write this as a V1. Now just do the calculation. X2 is -1, 2, 3. X2 dot V1, careful. For being extra careful, I'll just go ahead and write it in here. There's X2, -1, 2, 3, dot with V1, which is the same as X1, 1, -1, 2. V1 dotted with itself down here. Times the vector V1. So on the top of the fraction, I get -1 minus 2 plus 6. I get the other calculation I did before. I get 3. On the bottom, I get 1 plus 2 is 4. So now simplify. -1 minus 3/4 will be -7/4. 2 minus -3/4 will be 11/4. 3 minus 3/2 is 3/2. There is V2. as a check, V2 should be orthogonal to V1. V1 dot V2 dot these two vectors. You'll get -7/4 minus 11/4. Uh-oh, is this going to work out? It's easy to make a mistake. +3. So there's a mistake somewhere. Oh, whatever. Anybody see the mistake? I don't see it. Let's see what Mathematica produces.
The fraction 3/4 should be 3/6.
Yeah. At least one mistake, which is 1/2. I like these numbers better anyway. Not that that's the reason, but okay. So now let's try V1 dot V2. V1's up there, V2's down here. -3/2 minus 5/2 +4. Yeah, that looks better. -4 + 4 is 0. As I've said before, of course, all of this stuff takes time, but you know, it is to your benefit if you can make the time, if you can plan ahead to, during the lectures, when I have to go through a bunch of theoretical stuff, take the time to do a quick calculation to double check things with an example. I mean, this is not a super quick calculation. It's not terribly long either. It's not as long as the nonlinear system. You know, just make sure things work and make some sense. Now, again, you can make drawings to make sense out of this. But for the moment, we don't have time, in class at least. This does extend to more than 2 vectors. Notice the etc. there. It extends to p vectors. This stuff, the last thing I'll say today, this stuff generalizes in important ways for the content that comes after exam 4. Again, I mentioned this before. There's 3 main lines of things that happen after exam 4, last week and a half of class. The main things you need to be able to do calculations for on the final exam, stuff from the book, which includes more about nonlinear systems, things called Hamiltonian systems, for example, gradient systems, for another example, and chapter 6, Laplace transforms. But then I also do talk about more advanced things. Calculations with respect to the more advanced things just probably take too long in general to put on exams in class without a lot of help. So, and this is what I'm thinking of is something related to partial differential equations and Fourier series. If you've heard of those things before. The full calculations could be a 1-question exam, okay? And some people still may not finish. So to do full calculations with those is beyond the scope of what we would do on the final, but you should still try to understand the basic ideas well enough to answer true, false, multiple choice questions about them and do basic calculations of pieces of them. So that means you still need to see the lectures and get the basic idea of them. And it's related to this stuff, actually, because dot products generalize to something called inner products. Dot products on Rn generalizes to inner products on function spaces. So vector spaces and particular function spaces come back again. And the Gram-Schmidt process generalizes. And it's important in terms of understanding what's really going on with these Fourier series, which ultimately help you solve partial differential equations. Any questions about that? One more quick thing to say. With the nonlinear systems, should also say an important terminology to look for in the lectures are hyperbolic versus non-hyperbolic equilibrium points. Does that have to do with hyperbolas? No, actually. Hyperbolic equilibrium points are the ones that are easy to classify, like these two, where the Jacobian matrix has a non-zero determinant and also not purely imaginary eigenvalues. This equilibrium point, I didn't confirm with the calculation, but I would bet it's not hyperbolic. Actually, yeah, I could. If I plugged in 0, 0 into the Jacobian matrix back here, I get a column of zeros. And that would mean this matrix would have a determinant of 0, which is enough to say this is a non-hyperbolic equilibrium point. It's not easy to classify using theory. In practice, with pictures and enough careful pictures, you can sort of classify it, but based on the structure of the theory, you can't. So watch out for the term hyperbolic equilibrium point as well. Okay, homework due this Tuesday, tomorrow. The next assignment, which I will try to get up tomorrow morning, will be due the next Tuesday after Thanksgiving. Okay, and we'll end class there. Thanks.
Yeah, turn this in for CP.
Yeah, CP is ready for you to turn that in the first page.